Awesome. Thank you, Michael. Hi, I'm Samantha, and I'm here this month for our fused granular fabrication meeting, aka pellet printing. Um, and I'm here on behalf of Re3D to help support the meeting and the logistics. But know that if you are interested in pellet printing or fused granular fabrication, you by no means have to use our platform. You know, we're here to learn and grow together. So please tell your peers. Hopefully this is a great space just to share knowledge as you're all pioneers. Per usual, because we haven't heard otherwise that it's not working, we're going to go ahead and we are recording this. And we'll have a speaker from the community share a little bit about what she's been doing. And then we'll open it up for Q&A. We'll leave it open for a couple minutes in case people want to share a question that's recorded. It will be put on our YouTube channel. If you want to check it out later or share it. And then we'll turn the recording off just for general networking. But we are holding these. We're trying to hold them every month. We do have a roster of a couple people interested in presenting in the next couple months. But if you would like to present and share what you're doing, we'd love to get you on the calendar. Just reach out to Michael. He'll put his email and LinkedIn in here, and we can get you set up. But with that being said, we'll go ahead and kick things off. I'm really excited about this one. Full disclosure, they do have one of our printers, but we've just been blown away by all of the depth of the research that they've been doing. And I think you'll be really intrigued by Dr. Jessica Vold's presentation today. Jessica is the Assistant Professor of Engineering Entrepreneurship and Innovation at North Dakota State University. And she's an experienced research and development engineer with a demonstrated history of working in the biotechnology industry. She is skilled in composite materials, extrusion, injection molding, materials characterization, technical rating, finite element analysis, and systems engineering. So you'll find that she has a depth of expertise and is focused on mechanical engineering and materials science with a passion for innovation and entrepreneurship. She's also the 2023-24 Possibility Fellowship Advisor, which is a program organized by the Center for Entrepreneurship in Family Business. So with that in mind, I'll stop talking and turn it over to Dr. Vold so we can hear more about using local resources in extreme environments.
Perfect. Thank you, Samantha. Yeah, as Samantha said, I'm Dr. Jessica Vold. I'm an assistant professor here at North Dakota State University in Fargo, North Dakota. And I'm going to talk about advanced materials creation from local resources in extreme environments. I do have to give credit to two of my former grad students that really did the bulk of the research in this project. I really just guided them through what they were doing. So Christopher Matedich graduated a couple of years ago. He focused on one planetary body. And then Abigail Olson was another grad student that also graduated about 2 years ago to this day almost. And she focused on another planetary body throughout this work. So to kind of start with, when I say extreme environments, you might have a couple of things that pop into mind. One of them might be a scene like this, right? It's very cold. There's lots of ice. There's lots of water present in this picture, but it's in a solid state. It's frozen. And there's just really not a lot you can do with the resources in this particular environment. An environment that we are very familiar with here in Fargo, by the way. Maybe you think of something a little bit different than this. Maybe it looks more like this. It's a desert setting. It's dry, it's arid. There is a little bit of moisture here in this landscape, but not a lot of it. And one of the bigger concerns here is the sand itself that's present. It's very abrasive. And how do we take stuff from that sand or from anything that you can find in the area and make a usable material out of it to create parts? Another kind of extreme environment that maybe you might not think of is kind of war-torn areas of the world, or even just underdeveloped regions of the world that's very, very hard to get to if you need to create pieces, right? I need to replace a part that's broken. How do I do that in that particular environment? And while I will agree that all three of these environments are extreme, and there are all places that we would like to eventually work with in our technology, what I actually mean, which you may have hinted at by the picture there on the left side of my screen, is something more like this. This is the lunar surface. This is a mock-up of what NASA envisions a human presence looking like on the lunar surface. So you can see some landing sites, some launch sites. You can kind of see off there in the right side over here, kind of like a habitat type area where humans might be living. And so we have to ask ourselves, how do we create all of this infrastructure before a human ever lands on the moon, right? You can kind of see way back here, also on the left, kind of looks like a city back there. I also mean something like this. And this is what NASA kind of envisions the Martian surface looking like when we inhabit it with humans as well. You can kind of tell by this picture that they probably envision a lot of these structures to be additively created. And so what we really have to ask ourselves is, how do we create this building place, right, that you clearly are going to drive a vehicle up to and connect to, that protects humans from all of the things on the Martian surface? And to do that, we need to understand how to use the regolith. So that's all this unconsolidated rock and dust that's on the surface of the Martian planet, or on the moon as well. How do we take that and create a material out of it that we can create building structures with, new tools with, that type of thing? So when we think about that, there's a lot of concerns that we have in terms of long-term space missions. You know, we're very good at sending humans up into space for a short amount of time and then bringing them back home. But if we plan for them to live on an extraterrestrial body like the moon or Mars, they're going to be there for a very, very long time. And one of the bigger concerns is transportation, right? You can't just grab an Uber to the moon or an Uber to Mars. You got to leave the Earth at a very specific time, in a very, very specific window, in order to get to that planetary body in a timely manner that's also economically efficient, which might sound a little bit odd when it comes to thinking about space travel, because it's very, very expensive to travel into space as it is. But we're kind of limited into those windows. The atmosphere themselves on each of those bodies is also a concern. You get, the dark regions are very, very cold. The light regions are very, very hot. And we were talking extreme heat and extreme cold. And then that regolith that we talked about on the planetary surfaces is extremely abrasive. It's very, very much like sand in a desert, if not even worse than that, right? The particles are just very abrasive, almost like broken glass, like in terms of their abrasion. So it's very, very harsh on equipment and structures, right? We think about winds and that type of thing on those planetary bodies as well. So we're concerned with that regolith being abrasive. Radiation is the kind of the next big concern, especially for humans. And when we talk about radiation, we're talking about solar flares, galactic cosmic radiation, that type of thing. And exposure of that to humans can have long-term health impacts. And so how do we protect humans while they're up there, creating that barrier between the radiation in the planetary body and the habitat that they're actually living in? So it kind of raises our big question, right? How do we protect that human life, specifically on the moon and Mars? Obviously, this could translate to other extraterrestrial bodies. At some point in time, we'd also like to bring this back down to Earth. So thinking about the technology that we develop to create materials on an extraterrestrial body, being able to also deploy that into war-torn regions of the world or underdeveloped regions. Maybe it's a disaster-stricken region, big hurricane came through. How do we go out and start, building habitats to protect humans in with what's available on the surface? So we're going to look to in situ resource utilization, really just taking what's there on the ground and turning that into a usable material. And on the moon and Mars, specifically thinking about autonomous rovers and using them to build habitats. You can see down here another picture by NASA, what they kind of envision the building process looking like, right? We've got something kind of akin to a front loader or bulldozer or something here that's kind of collecting the regolith off the surface. And then it's probably adding it to this other rover over here that's very clearly additively manufacturing a habitat. Now, there's a human here in this picture, kind of as an astronaut here, but can we do this without a human ever being there? And ultimately, what we're looking to do is, can I do this where I don't really need any resources from Earth, right? We talked about those launch windows. We talked about how expensive it is to launch materials into space. So can I do it with something that's there on the surface, right? I can launch this robot that's additive manufacturing. I can launch this loader here, and if all the materials that they need to do their jobs are from the surface, then I can do everything I need there on the planetary body. The other thing, kind of advantage to this as well, is it allows for rapid replacement of broken tools or objects, right? As much as it would be really cool to be able to just, order a part off of Amazon and have it delivered to the moon or Mars, I just can't do that. And so if I break a tool, I've got to replace it with the resources I have on the planetary body. And so we're hoping that we can do that, using the regolith and creating polymers and composites and then additively manufacturing with those materials. So I'm sure as you can imagine, there has been a lot of work that has been done up until this point on materials on planetary bodies. A lot of them have looked at if I take the regolith and I add just a small amount of polymer, thinking less than 5%, I can take that, I can compress it into bricks. They're really, really good at shielding humans from radiation. The regolith on the surface is great at doing that in the first place. So I can use that to our advantage. The issue with this, right, is one, where's the polymer come from, right? The regolith, there's not just polymer I can pull out of it on the surface. So what polymer am I using? The second issue with this is that compression molding is a traditional manufacturing process, and I need relatively large pieces of equipment to do the compression molding process. I have to be able to put materials in, compress them, pull whatever is created out of it, thinking like bricks and that type of thing, and then place them into my building. I'm sure we can probably build a lot of different autonomous rovers that can do this, but it's getting to be very, very complex to do that. You need large pieces of equipment that I think we could be a little bit more efficient with our space and the vehicles that we launch onto those planetary bodies. The next thing is kind of in situ polymerization, thinking about those polymers that we're adding to the regolith to turn them into a brick. There are theoretical paths to polymers on the Martian surface. We can pull the building blocks for polyimides, polyethylene, and polypropylene from Martian regolith. To date, this is really just theoretical. There's been very, very little experimental work that has been done on this. There's been a couple or handful of experimental studies that have worked with like polypropylene and a polyethylene, but not very many of them. So there's a lot of work that has to be done here. The lunar surface, on the other hand, is really just void of anything. It's very desolate. There's nothing chemically there. We can't even pull the most fundamental building block of a polymer out of the lunar surface. And so we have to get a little bit more creative on the moon to think about what materials can we actually create with that regolith in order to protect our humans. There has been some work done on regolith-filled composites. So this work has been done with PLA in both the moon and the Mars. And the biggest concern with most of these studies is they're only using 5 to 10% regolith. They get very similar flexural strength to that of PLA, which is promising result, right? It kind of lends to it could be potentially a building material. But the issue with this is you still need 90 to 95% polymer in that composite. And if you're not creating that from a resource right there on the surface, you have to bring that material with you from Earth. And as we just talked about with the Martian, we were talking about polyimides, polyethylenes, and polypropylenes. It's not a polylactic acid, right? It's not PLA. And so where do we get that polymer from? And so can we increase the amount of regolith that we actually put into these composites to minimize the amount of material that comes from Earth? I'm sure as you can imagine, some people have looked at additive manufacturing with these composite materials. There's actually been a study here, this picture is from the study, that they created a filament with their composites, and then they just traditionally FDM printed with them on a desktop FDM printer, which is great, but that's an added step, right? If I'm looking to be effective and efficient in the way that I create materials, I don't want to have to create my composite, create the pellets, create the filament, and then go and 3D print with it in an FDM setting. And so thinking more along the lines of, is there more of kind of a singular process where I can take the material, turn it into a composite material that I can print with, and then just directly print with that into the shape that I need. My other issue with this study, which it was a good study that we learned a lot from. They again only looked at 5 to 10 weight% of regolith in their polyethylenes. And when they say regolith or regolith simulant in this study, they don't actually mean a mixed mineral composite. They mean basalt, because all they did was they used a pure basalt material as the filler in their composite materials. And so when we think about the chemical makeup of regolith on both the moon and Mars, it really truly is a mixed mineral material, right? There's lots of different compounds in that regolith. And so we need to understand how do each of them interact with the polymers, how do each of them interact with each other, and what are the material properties we get in the end, because they are going to be different based upon how the minerals all react with the polymers. There has been some studies that have looked at how do we increase that loading of our regolith into our composite material. So there's been some studies that have looked at like 74% roughly regolith, and they've kind of turned them into microtruss structures. There's also been some work on, can I just use a laser to actually melt the regolith, right, and sinter it together into a brick? Both have been very successful, but they've had very, very high porosity. And that really ultimately leads to poor mechanical performance, which ultimately means we just can't trust that material in terms of a building material to protect our human life. So there has been some work on structural materials as well. One of them was a really cool study where they looked at, I have 100% regolith on one side, and that functionally gets graded to 100% metal on the other side of that particular part. And it's a really neat idea if we can make it work, right? We can utilize the regolith on one side to do our radiation shielding, and then we have our metal on the other side that we know is a structural material. We know how it performs in buildings and that type of situation. The issue with that is those two materials, regolith and metal, are very, very incompatible when it comes to their thermal expansion. And so we end up with a compromised part in the end because of the differences in their thermal expansions. There's also been some work thinking about more structures, right? You saw that image in the last slide of what NASA kind of envisions of additively manufacturing buildings, of creating sulfur concrete. And there are paths to sulfur concrete on the Martian surface. The issue with that is we can create with it. We know we can build materials with it because we've tested it here on Earth. But sulfur concrete in the presence of oxygen or moisture produces toxic gases, which are harmful to humans for obvious reasons. And so we need to be able to protect humans from that potential off-gassing. There's been some talk of using like a plaster type substance to cover the inside of those buildings. But the plaster itself is brittle, right? Humans, you knock into the wall, that plaster is going to get knocked off, chipped away, and at some point in time can expose the sulfur concrete beneath it. And then again, you're in a situation where you potentially have some off-gassing. So this kind of leads us to a lot of questions, right? How do we maximize the use of our local resources? How do we minimize the amount of material that we need to bring from Earth in order to create these materials? Can we take the regolith on the surface and extract polymers out of it, right? On Mars, we think we can. And we've got a couple of potential polymers to work with. On the moon, it's going to be more of, can we take the materials that are already brought from Earth? Can we use the plant material once we have humans there and they're growing plant matter? Can we turn that into a PLA, PHA? Can we use a mixed recycled stream of polymers from packages and that kind of thing, and recycle them into then building materials or materials just to create new tools with, that sort of thing. And then the last question, which is what a lot of our work focused on, is when we look at a planetary body and we look at the various regions that we take our regolith from, they have slightly different chemical compositions. They have slightly different physical structures as well. Does that impact the mechanical properties if we were to create a composite material with those materials? So what we did was we worked with Space Resource Technologies. They used to be called Exolith Lab. They're a spinoff of a university lab at Central Florida. And they have been approved by NASA to create regolith simulants. Unfortunately, we are not cool enough up here to be able to work with actual regolith that came from Mars and the moon. I would be thrilled if I could, but I can't. So we have these simulants. They are chemically the same, so that NASA has looked at the chemical makeup of the regolith on each planetary body in various different locations. And then they're also physically thought to be the same as well. So they've analyzed some of the regolith that has been brought back, and they believe that this is the closest thing we can get to actual regolith. So for Mars here, we looked at 4 different regions. We looked at a global simulant that researchers believe kind of mimics the regolith that's kind of around the entire planet, for the most part, kind of an average simulant, if you will. We looked at one that has a little bit more clay content into it. We also looked at one that has a little bit more sulfate as part of the chemical makeup. And then we also looked at some that came from the J0 delta. So that's, again, a little bit different chemical makeup. And as you can see, they're very different colors, which is indicative of the chemical, the mineral makeup that goes into them. For Mars, looking at kind of the theoretical paths to polymers, we chose to go with polypropylene, which if you are into additive manufacturing, which I hope most of you are, you know is very, very challenging to work with. But we were able to successfully print with polypropylene. And this is a Phillips 66 polypropylene, just a neat polymer, nothing special about it. The big thing we looked at when choosing this was the melt flow index, making sure it was kind of suitable for additive manufacturing, wasn't going to drool out of the nozzle or anything like that. On the lunar side, we looked at 2 different locations for our simulants. We looked at the highlands, and then we also looked at the mare, kind of the low-lying delta regions of the lunar surface. And then we looked at 2 different grind sizes. So these first 2, LHS1 and LMS1, are just the regolith as they see it on the planetary body. So it has not been sieved. It's got this kind of the standard particle distribution that they have found from samples of lunar regolith. And then the other 2, LHS1D and LMS1D, that's the dust version of both of those locations. So they've taken the regolith, they've sieved it down just a little bit to be a finer particle, a much narrower particle distribution. And we kind of looked here as well at not just as what the location does to material properties, but does the particle size as well impact those mechanical properties. For the moon, since we really don't see a path to polymers in terms of the regolith itself, we kind of turned to, we know once there's humans there, they're going to grow plants. And can we take that plant matter that's left over and turn that into a bio-based polymer? So in this case, we're looking at a PLA. So we're doing NGO biopolymer. It's a 3D 700. It's a grade of PLA specifically designed for large area additive manufacturing, which what we're doing with our big pellet fed printer from Re3D. So in this case, we did do studies from all the way from 10% loading, weight percent loading to 40 weight percent loading. We found that the mechanical property spread really didn't change a lot across 10 to 40 weight percent. And so we chose to move forward with the 40 weight percent regolith loading within our polymers to maximize the amount of regolith used and minimize the amount of polymer. And I'll talk about in a little bit that we'd like to push that envelope even farther past the 40%. So for our processing, we first did do some extrusion. So we're using an 18mm twin screw co-rotating extruder. It's made by Leistridge. It's a German German manufactured extruder. And then we've got down here at the end of it, we've got a pelletizer. So we did turn it into pellets before 3D printing with it. We did do some injection molding just to do a comparison between what the material properties would be like in a traditional earth-based kind of manufacturing setting and seeing then how does it change when we go to additive manufacturing. So we're using a 100-ton, it's a servo-electric injection molder, and we're creating rectangular dog bone specimens like you can see up here, or sorry, rectangular specimens. And then we also do dog bone specimens that I don't have a picture of on this slide. And then we also did some additive manufacturing. As Samantha said, we do have a Re3D Terabot X pellet fed printer. If I'm not mistaken, I believe it's also the very first commercially made Terabot X that we've had here for a couple of years. And we basically 3D print the exact same specimens that we injection mold. There are some slight differences to our tensile bars, the dog bones, just because there ends up being some stress concentration points when we additively manufacture the exact same shape that comes from injection molding, but they're relatively similar. And in terms of standards, they do meet the same standards. And then we did some testing on these. In this work, we're focused mostly on tensile testing, flexural testing, and then IZOD impact testing. We do want to look at compression testing. As you can imagine, that's very important when it comes to like habitats, structural materials, that type of thing. We unfortunately just did not have the grips in place at the time of this work to do the compression molding. We did print the specimens, we just didn't get to get them tested within the labs. So we do plan to do that at some point in time. I just threw a slide in here with some of the print settings. I think the biggest thing I'm going to point out here is the E number is the one thing that changed the most for us. On the Martian side, it really didn't vary a whole lot between these materials to get 100% infill in the parts. On the lunar side, though, the mare dust, which was really, really interesting, we had to increase the E number to 90. It was a significant change to get that material to print properly. And we believe that led to a couple of, like minute differences in mechanical properties in the end. But other than that, the print settings were very, very, kind of similar across the board for both of them. Obviously, different temperatures for the different materials, that type of thing. Our polypropylene, we did get to stick to our bed using the Magic Glue PP. Basically, it's a glue stick for additive manufacturing. So we look at some of our results. I do compare both injection molding to additive manufacturing. That's kind of the biggest thing that we're looking for within our materials. With our Martian composites here, again, we're looking at 40 weight% loading within our polypropylene. We see very, very similar results to what we'd expect, right? We add 40 weight%. We're not seeing a whole lot of change within our tensile strength. Our tensile modulus also doesn't change a whole lot, which is something that we would expect to happen with that rigid filler. But just through observations, one thing that we noticed was the sulfate. So this MGS1S is the regolith that has a little bit more sulfate in it than the rest of them. Had a really, really poor melt strength, to the point that it was nearly impossible to pull strands and create our pellets in extrusion. And in injection molding, it just drooled out the nozzle at the end of our injection molder. It was very, very difficult to work with. You know, it's not an unheard of occurrence when you add in a mineral filler into a polymer. Those minerals retain heat. And so we do expect to have like the melt behavior be a little bit different. And we can usually counteract that with some cushions that we add into our injection molding. And we just couldn't overcome that with the sulfate material. So based on that and a couple of other kind of observations within other mechanical testing, we chose not to move forward with the sulfate or the J0 delta simulant. So we only moved with our global, our MGS1, and then that simulant had a little bit more clay into it. We took those two simulants and moved them forward to our additive manufacturing testing. So we did additive manufacture our tensile bars, and when we got to these results, we had some really, really interesting things occur. The very first thing that we noticed was our neat polypropylene, right, that had, modulus of, I don't know, around 0.75 gigapascals roughly, was now all of a sudden above 1.5 gigapascals. And we thought, that's really interesting. We made our material stiffer when we additively manufactured with it. And so there's kind of some really interesting things that kind of occurred with this. Or my student dug into it a little bit more. And what we really think happened is in the slow kind of process of additively manufacturing, right? When we think about injection molding, it's a really fast injection of the material. It flows very quickly out into the mold. You get some chain alignment of the polymers just because of the flow and how fast it is. But in reality, it's really an isotropic material, right? That there's really chains going in every different direction. But we believe with the additive manufacturing and the way that our Terabot X is working is we're getting a lot more chain alignment in the printed part, in the direction of the print. And so we see a much stiffer material from our neat polymer. So there's a little bit of work we need to do there to kind of figure out what's really happening. We can do some testing by printing in different directions and that kind of thing. We haven't gotten to that work quite yet. The planetary location very much did influence our tensile performance. So that tells us with Mars, at least, we need to be careful of where we're at on the planet and thinking very carefully about how much regolith we put into that polymer, or what our expectations are of the mechanical properties or performance of that material. And then we also noticed, right, so we see some differences here in the tensile strength, which isn't unheard of. There are some differences in the tensile modulus as well. But just based off of observations of the additive manufacturing process, we believe there are some secondary reactions occurring in that open to atmosphere processing that are potentially hindering our mechanical properties in the end. And we'll look at something like that. We'll talk about that here in just a little bit. We moved over to the lunar surface as well. And there's definitely an influence over the strength. There's a minor impact on the modulus for the injection molding in terms of the lunar location. There's really not a lot within these properties that was kind of surprising to us. I think the biggest thing that we didn't expect was that the particle size didn't really have an impact on the mechanical properties. for the lunar composites. We very much expected that smaller particle size to kind of have an influence over the strength and the modulus, but it really didn't. This Mare Dust 40, that was the one that we had to really increase that E number with to get the material to come out of the extruder and produce a part that didn't have visible voids in it. We were looking for 100% infill. Really increase the properties, right? I mean, these are much higher than what we saw even from injection molding. And certainly much higher than the neat or the other composites. And so we think what's happening here is that because we've increased that E number to get a visibly 100% infilled part, we're actually getting fewer voids within those particular parts. And then unfortunately, Abby, who did the lunar work, didn't get a chance to do a lot of microscopy before she graduated. And that's one thing that my students going forward would like to look into, is doing some microscopy. So mounting of those samples and doing some polishing to see, is there a higher void content in the non-Mare dust samples, to see if that really is impacting our mechanical properties. Our fluxural strengths for the Martian, again, we saw results very similar to what we expected them to be. Our planetary location had no influence on the modulus. It had some very minor influences on the strength of the part, but it would not be like a huge consideration when thinking about, where do I take the regolith from to create these habitat materials from. There was an influence on both strength and modulus from the additive manufacturing side. Again, I think some of that might just come in inherently from the way we actually produce those parts. And so if we play a little bit more with some of those printing parameters, making sure we don't have voids within the part when like we think it should be 100% infill, but there's actually some voids, we might be able to manipulate some of those material properties again. And then again, that chain alignment in the printing direction is coming into play here with our polypropylene. The neat specimens themselves have, I don't know, higher properties when you additively manufacture with them, which is not what we expected to see at all. All right, so moving on to our lunar in terms of our fluxural strength. This Highlands dust, which was really surprising, had this really, really high standard deviation. When we think about materials properties, we're thinking like something less than 10%, right, is what we're targeting here within these parts. And it was extremely high. And so Abby looked into this a little bit, and we believe that the polymer itself is absorbing some of the additives, or there's some uneven wetting between the polymers and the regolith simulant. And it's kind of this inverse effect. So as the particle size goes down, this effect goes up, which would explain why our Highlands materials do very well. But then when we sieve them down into the dust part of that simulant, we're getting this very, very high standard deviation. So, and we're not really sure, we got to do some more experimentation into this. And this was an effect that we saw in additive manufacturing as well with some of our parts, which I think this, with the Highlands might just be part of the additive manufacturing process. But the Mare dust, again, showed a really high standard deviation when it came to our fluxural strength. Our lunar region and the particle size, in this case, had absolutely no impact on the strength values for additive manufacturing. Which is really promising to see. Again, we wouldn't necessarily have to think about the region necessarily. But they had a very, very high influence on the modulus. So the stiffness of those materials, which I think might be partly chain alignment, some of that absorption of the additives or the uneven wetting as well could be coming into a play with those materials. We also did some impact toughness. So thinking about, if you build a habitat, something hits it, right? Very, very common with humans being around, and even just in a space environment, you can have, micro meteorites and stuff like that coming and hitting the structures. So thinking about the impact toughness. This graph here, my students created these graphs, and this one did show that we did do 10 to 40 weight % of the Martian regolith in here. We were focused on the 40 weight % though when it came to our additive manufacturing. Our injection molding showed no evidence of influence from the planetary location, which was really interesting to see. It had a little bit of influence in other properties we thought would lead to an influence and impact, but it didn't. But the additive manufacturing did show an influence based on the planetary location. And so it will be consideration when we do think about building materials, where it comes from. And then again, we think that alignment, it's just the alignment of this chain is kind of preventing horizontal chain entanglement. And so our polymer chains are reacting a little bit differently to that, absorbing that energy, which is why, again, our neat polymer, it went from, I don't know, like 9.4 roughly kilojoules per square meter for impact toughness to over 16, which was just really surprising in here. So we do want to look more into that in the future as we go forward. For our lunar, very, very kind of what we expected to happen. Our impact strengths changed a little bit when we went from injection molding to additive manufacturing. We had minor influences from the lunar location on toughness, but that particle size did not have an influence, which tells us that we don't need to, take that extra step of trying to sieve the regolith down into a much, narrow particle distribution. We can just take it as it is off the planet, and turn that into usable materials. And have relatively, good mechanical properties in terms of the neat polymer. In this case, with additive manufacture, we saw a little bit better impact resistance with our composites than we did with our neat polymer, which was also a very promising result to see. So some of the observations, which I think is kind of more the interesting part of this work, we talked about the extradite, that kind of low melt strength with our sulfate composite. And so we kind of ruled that out in terms of moving on to additive manufacturing during the injection molding. But even the composites that we did additively manufacture with, we saw this swelling effect when it came out of the 3D printer. And interestingly enough, as we increased our loadings, that increased as well, right? And as I said earlier, it's not uncommon, right? We're adding a mineral-filled polymer. It retains heat, right? The mineral does. And so you're going to see it kind of thermally expand a little bit. But it was kind of an extreme kind of swelling, right? That we did see with the sulfate, but even with the other, like the global simulant and that clay-filled simulant that we printed with, to the point that we almost had this surface that looked like we had foamed our material as opposed to 3D printed with it. So this top picture up here is a Martian part, and you can see the surface of this part is very, very pitted. And that all occurred in the additive manufacturing process, right? So when we extruded it out and laid down those layers, it was very, very foamy, which we think is impacting the mechanical properties. And so we think if we can reduce the foaming effect, create a more smooth surface finish on these parts, we can get better mechanical properties in the end, which would make these even more viable materials when we're thinking about producing parts on the Martian or the lunar surface. Interestingly enough, we did not see this on the lunar parts, right? So this is our neat PLA, and then all of our 40 weight% filled polymers. And they have really nice surface finishes, right? You can see some of the raster lines here in our 3D printed parts, but for the most part, they looked great. And so it's really an issue with our Martian simulants, and they do have different minerals than the lunar simulants do themselves. And so we believe there are some secondary reactions occurring within our Martian composites. And something that in injection molding, when we think about the force used to mold the materials and kind of push the air, expel the air out of the cavity, maybe some of those reactions, the gases produced in those reactions are being removed from the mold. But in an open to atmosphere process like additive manufacturing, we can't get that to come out of our part. And so what can we do to prevent that foaming mechanism from the start? So we did do some microscopy images, just kind of look at these parts and think about, what are we looking at? Are we actually getting voids, that type of thing? Are the voids themselves from particles that have fallen out? Are they voids just like within the part? Do they come from, between raster lines, between layer to layer adhesion, kind of where those voids might come? So this picture here on the left is our injection molded specimen. It looks exactly like we'd expect it to, right? So all these little particles are the various different minerals within our simulant. And these images are all at 10x. Each of the little length bars are 200 microns. And then these other two here on the right are additive manufacturing specimens. What's really, really interesting is to note the voids within them, right? So we have very large voids within this part that we do not see within our injection molded part. You do see some dark, smaller specimens. Those are actually like hard minerals that show up dark in our microscopy. So there are no voids within this part. But in our injection or additive manufactured part, these are voids. There is no particle that's present within those regions of this part. And so where do they come from? Some of them we believe are particles that have fallen out in the polishing process or the cutting process. So these just take broken specimens from impact testing, flexural testing, and something like that. We cast them in a thermoset and then we polish them before we look at them under a microscope. And so some of them have fallen out, which indicates to us that there is a lack of adhesion between the particle and the polymer. That one is due to like uneven wetting, but there should be a good bond between the mineral and the polymer, because we see in injection molding that there is a good bond between those materials. Or is there some sort of reaction happening that is off-gassing, and that gas is getting trapped around the particles themselves, and then that's producing a weak spot, right? Stress concentration within our part, that then, that particle is where it fails. So we're not really sure what's happening there. We have some theories about what might be happening. We do have some experiments planned at the moment to kind of figure out what are those reactions? How can we prevent them from happening to make sure that our additive manufacturing materials or parts are as good as we possibly can make them? So the other really interesting thing that we learned when we did this was you'll notice there are no distinguishable roster lines within either one of these microscopy images. So the parts looked phenomenal in terms of, the material kind of adhering together. We also couldn't, as we kind of polished through the specimen, could not find like obvious places where it was layer to layer adhesion that it might produce a weak point within the material. So it printed very, very well. We just got to be able to figure out why it's kind of like this foaming, that's kind of what we're calling it, is occurring in the processing. So for us, kind of what's next is understanding how those minerals within the regolith or the simulants kind of interact with one another, how they interact with the polymers in terms of composite processing. So we've got a current NASA EPSCoR project that's looking at that and kind of trying to start to figure out breaking down that simulant mineral by mineral and figuring out what's happening with each of those. We also want to go back, right? We kind of put a pin in J0 in the sulfate regolith for Mars. We want to circle back to that and see, can we do something with those to make it a melt strength that we can actually process with, right? One that we can create pellets with, that we can then 3D print with, we can injection mold with. And so based on what we learn in this NASA EPSCoR project that's looking at the minerals in the regolith, this might get written into a future proposal kind of for future funding to look at what's going to happen with it. So then we really don't have to worry about where on the planet are we taking that regolith from. And then the last thing I'm going to look at is on the lunar side of it, right? We had very good success with those material properties. They printed beautifully. It's PLA. I've expected to print beautifully, but you just never know with the minerals that go into it. Now we want to take a kind of a step away from PLA and think about, okay, a human's there on the lunar surface. They're growing these plants. We could create some PLA, potentially some PHA, but they obviously have packages that have come from Earth on, supply missions and that type of thing. And what can we do with those packages? Are going to be a mixed stream of different polymers? Can we take those polymers and can we create usable composite materials that could, replace tools, or if it's structural building, right? Maybe I have to fix part of a building. Can I do that with additive manufacturing? That type of thing. So that's kind of where we're focused on in the future. And with that, I'll thank some of the sponsors for our project. NASA EPSCoR has been a fantastic support for our project, as the North Dakota EPSCoR and the NASA EPSCoR programs both have been. And then Bamberger Polymers, Phillips 66, and Space Resource Technologies have all been fantastic in supplying materials to start with, just to see, could we do proof of concept before we actually went in and bought a whole lot of materials to work with. And so with that, I would happily answer questions from anybody.
Thanks, Jessica, for such an amazing presentation. There were a lot of outcomes I found surprising, and I'm sure other people that were listening did as well. It looks like Dawood has a question he just posted in chat if you're able to see it.
I am. Okay. For the test samples made by FGF process, was a specific standard followed during their preparation? Was the B2B layer adhesion strength tested? Yeah, that's a really good question. We did not test layer to layer adhesion for our specimens. It is something we would like to do moving forward. Um, we we thought that would be more of an issue than it was in our testing. We thought a lot of our mechanical properties would be like, oh, it's because the layer adhesion isn't the greatest, especially with our polypropylene. But then looking at them under a microscope, it was not as big of an issue as we thought it was going to be. And so we kind of put that on the back burner for the moment. We were more concerned about those voids we saw in our microscopy images and figuring out why that had happened. Because they were very clearly, like if we look at them, they were very clearly not because it's from layer to layer or, you know, roster to roster like adhesion. But that is something we need to look at. And then in terms of standards followed for printing, we did not know. The standards we followed were for the geometry and the shape of the specimens in terms of ASTM standards. How did you control for bed adhesion and warping or shrinkage during printing? That's a great question, Charlotte. So for our PLA, we just heated the bed, which I think, oh, I should just exit this presentation. There is. So we heated it, the bed temperature is 50 degrees centigrade for our PLA, and it did beautifully. We had no issues with adhesion at all with those parts. And then for our polypropylene on the Martian side, we had 105 degrees C print bed, and then we used the Magic Glue PP. So it's basically a glue stick to adhere it. And that worked absolutely wonderfully to get the polypropylene to adhere to the bed. We thankfully at the time had a local company that produced filament. So 3Dom Fuel was in town. I think they're back in town now, and they conveniently had a shop in town that we could just walk over there and buy Magic Glue PP when we needed it. So it was fantastic. That stuff is amazing. A coworker now, I believe, is just using like Elmer's glue sticks to do it, and he's had some pretty good luck with that too. So. How did you define the sidewalls for additive manufacturing dog bone samples? Some labs use special cutters or machine operations to cut the sidewalls, as opposed to letting the manufacturing process define the sidewalls of the dog. Oh, we just printed them. That's all we did. So we put the shape in. The biggest thing that we had to control, if I go back to sorry, I'm like flying through these slides. So the biggest thing we had to control was the slicer that we're using. So we're using Simplify 3D. It wanted to put like the starting point of every round, like right here in the middle of our specimen, which it's a stress concentration, so they naturally will fail there. So we had to force it to start them at the top in the grip section. And that is the only thing we had to force it to do. Otherwise, our sidewalls are just what's printed. So really trying to mimic like very little interaction with what's been produced and the performance of it. You know, thinking about like as few processes as we can, because we're not gonna be able to do that in situ on either of those planetary bodies. So.
And what was the tallest object that you printed with PP? The PP blend, sorry.
I believe it would just be our test specimens. So they're about 3 to 4 millimeters thick. I don't think Christopher printed compression specimens for his because we knew we couldn't test them for him. Abby did test, or she didn't test, she printed compression cylinders, and they're probably 15, 20 millimeters tall. So, and they did great. They look awesome. I really want to test them, but we haven't tested them yet.
Hey,
That's
Brock.
so cool to hear.
How you doing?
Good, how are you?
Got to my hotel.
Very good. Are you in Iowa?
Yep.
How was it? How's the trip? Easy? It's okay?
Well, they didn't have any cars. So I had to
Oh,
wait.
Luke, I think your microphone is on. Awesome.
Oh, there he muted himself.
Yeah. Well, does anyone else have a question while we have the recording on? If not, we'll turn it off. Okay, I think we can turn. Oh, we got one more question from Dr.
Oh.